So constrained and unconstrained optimization. طبعا unconstrained optimization becomes very simple. There is no problem, and if we have some constraints, the problem becomes more complex. Okay, so you have here the unconstrained optimization problem. You have objective function, or we call it cost function. You need to minimize. And then the necessary condition and sufficient condition is to have derivative, first derivative equal to 0, and the second derivative equal to greater than 0. So you have local A minima or maxima?
Minima.
Local minima. If this is less than 0, يبقى local maxima.
Yes.
This is local maxima. This is local maxima. And this is local minima. This is local minima. And this is also local maxima. If the second derivative equal, that means this point is a reflection point or inflection point. So you may have the function as such. So the derivative here equal to 0. Second derivative also equal to 0, but this point is not local maxima or local minima. It is inflection point, as we discussed earlier. Okay, so if we expand this for more than one variable, if you have different variables here, so again the condition of the first derivative equal to 0 with respect to all variables, and then second derivative becomes a Hessian matrix, and you can formula Hessian matrix very simple. You take the derivative with respect to x1, and you take the second derivative also with respect to x1, here with respect to x1 and x2, and so on. So you can form this Hessian matrix, and you can check the eigenvalues of the Hessian matrix. If the eigenvalue is greater than 0, in this case you have local minima, as we have. You have here very simple example, and we defined it. This is Hessian matrix, and this is the eigenvalue. So that is greater than 0. So this value is another very simple example we have covered already. First derivative equal to 0. This is a Hessian matrix, and we found this is the minimum value of this. Now, if we have a constraint, constraints could be equality constraints or inequality constraints. Let us start with the equality constraints. Here you have cost function you need to minimize, but subject to, provided that the solution that you will get from here must satisfy this condition. This constraints must satisfy this constraints, and this function equal to 0. So this is the optimization problem with equality constraints. How to handle these constraints in order to solve this problem? The idea here is to convert the problem from being constrained problem to unconstrained problem. If we have a way to incorporate this equality constraints here in the objective function or in the cost function, if we can incorporate this constraints here in the objective function, and we expand this function to include the constraint here, in this case we can say, and we have now unconstrained optimization problem. This method of incorporating these constraints here in the objective function is called Lagrangian method. And you have this constraints here, and you multiply it by what we call the Lagrange multiplier. And you multiply this here, you add here this plus, you can say that this is, okay, let us convert this to plus lambda times GI. So we have now new objective function or new cost function which is expanded by including this constraints here. This called Lagrangian L, and this called Lagrangian multiplier. So in this case, if you think about it, we increase the number of variables that we have. We have x1, x2 up to xn. We need those, and also we need lambda in this case. Lambda is a variable. So we convert the problem from being constrained to unconstrained at the expense of increasing the variables by one. ممكن by 1 or 2 or 3, and you can have here several equality constraints, right? So you can have here lambda I, and this if we have 3 constraints, but we have 3 lambdas here in addition to the main variables here. So you convert it to unconstrained, but you have to pay the price. The price here is increasing the number of variables by number of constraints here. So this is called Lagrange multiplier, and as we will see here, we expand the function, cost function, by these terms, and the k here is the number of constraints that we have. So let me ask you, in our problem, which is the economic switch, what do you think the equality constraints that we have in this problem? Economic switch, we formulated earlier, last class. Muhammad Hassan?
Total cost equals the losses plus the load.
You mean a total generation?
Yes.
Total generation, summation of BGI for all machines, any machines we have in the system, only generators, summation of BG equal to B demand plus losses. Okay, so this is equality constraint. Summation of BG minus BD minus losses equal to 0. So this is equality constraints in the economic switch problem. Of course, as we mentioned, then we will relax the problem at the beginning. We consider system losses equal to 0. So we will not consider the network constraints here. So summation of BG minus BD equal to 0. This is the equality constraints in economic switch problem. So K, the number of equality constraints. L is augmented objective function. You expand it. It's called Lagrangian, and lambda is Lagrangian multiplier. So these are the problem now. The problem now is unconstrained. So you will proceed as usual. You get the first derivative of L, partial L by partial, you have here f of x by partial x, and also partial L by partial lambda. And the lambda here becomes a variable, right? So this is equal to 0. طبعا ممكن يكون الاكس دي 10 15 جنريتور، فده partial L و partial BG1 x1 x2 x3 and so on, and you have here some constraints for lambda 1 lambda 2 lambda 3 and so on. So but all the first derivatives with respect to all variables equal to 0, and then we can solve to get x and lambda that satisfy these conditions, and we can search for the Hessian matrix, and we get the eigenvalue of the Hessian matrix, and if it is local minima, then it becomes greater than 0. So lambda is positive. Don't mix here. Question أنا قلت lambda لأنه lambda here is confusing a little bit. This lambda is different than this lambda. Okay, this lambda is a Lagrange multiplier. This is a multiplier. إنما ديت الإيه؟ دي الأيجن values. There is no link between them. فخلينا أكتبها ايج of h, eigen value of h، عشان ما don't confuse إنه this lambda has nothing to do with this. Lambda here is in the problem formulation is the Lagrange multiplier for the Hessian matrix. It is the eigenvalues of Hessian matrix. Okay. Okay, so the necessary conditions for optimality and lambda L, partial L by partial X equal to 0, xi, x1, 2, 3, partial L by partial lambda 1, 2, 3 also equal to 0. Of course, you have this L equal to F plus lambda G. So you have here, and this is summation of lambda G, it depends on how many constraint you have. So partial L by partial X equal to partial F by partial X. Summation here you have lambda I plus GI GXI. This is a derivative with respect to X, and this is a derivative with respect to lambda. When you have lambda I is different, or lambda 1 is different than lambda 2. And if you expand this will be F. If you have more than one constraints, so it is lambda 1 G1 plus lambda 2 G2 plus lambda 3 G3. So when you get the derivative with respect to lambda 1, it becomes a G1. Partial L by partial lambda 2, this is equal to 0. There is no lambda here in this function, and this is 0, and this is becomes also G2, and this is becomes 0. So partial L by partial lambda equal to G. Okay. So these are the necessary conditions for optimality, and then you can solve. You have here, in principle, you can solve, and we have here number of equations equal to the number of X, and here also we have number of equations equal to the number of lambda. So you have number of equations in general equal to the number of variables. So in principle, you can solve to find the values of X and lambda. Let us take a very simple example here, to show you how to incorporate this equality constraints in the objective function. Use the Lagrange multiplier method to determine the minimum distance from the origin of the XY plane to a circle described below. Now we need to find the minimum distance between the origin and this circle. Okay, we need to measure the distance and we need to minimize it. So we have here, we need the point on the circle. So the circle equation, this circle equation is x minus 8 square plus y minus 6 square equal to 25. This is the equation of the circle, and we need to search for a point here on the equation or in the circle to minimize the distance between the circle and the origin. Okay, so what do you think the distance would be? And what is the function here? What distance? Assume that you have any variable, any point here. This point is xy. The coordinate or ordinate of this is xy. Omar Abdurrahman, do you have a question?
No, it will be the equation of the circle itself.
ايه البروبلم في equation?
No, you said what's the distance?
نعم, the distance between the origin point.
Yes.
And what did we do?
Circle.
Between the origin point and the circle. What you can do is you can say the distance between any point. Let us say any point here is xy. The coordinate is xy. So the distance between the origin and this point is d equal to the cost function equal to what? Square root of x square plus y square, right? Or we can write f square equal to x square plus y square. This is the distance. Am I right or not?
Yes.
So we need to minimize this distance, provided that in this point, x and y satisfy the equation of the circle. And this point is one of the point of on the circle. So this is the cost function and this is the constraint. So f of x is x equal to x squared plus y squared, and this is could be the distance square. And the problem can be formulated as such. Minimize x squared plus y squared, provided that
Square.
function must
It's square.
Square root, you mean?
Yeah.
Yeah, distance equal to square root of x squared plus y squared. Okay. Here, yeah, here you can, what we can do is, let me ask you, if we consider the square root, does it affect the result?
Not that much, because if we take x2 and the y3,
it will not affect the results.
Yeah.
If you minimize this or you minimize x square plus y square directly. لانك انت ان الديستانس دي دايما بوزيتيف, right? Distance is positive right away. So if the value is for example مثلا 2, لو distance 2 او لو distance has any value, if you need to minimize, it will not affect the result. Is it clear? What I mean is, for example, if we have
x2 والy3 4, لو اخذنا ال x for example 2 and y3
والy3
4 بلس 9 هذه فيها 13 سكوير روت في 13
ودي بتبقى الديستانس سكوير روت اوف 13, رايت؟
ايوه تقريبا 3.6
ماشي, the value is okay 3.6. Now if this value is higher than 13, لو الفاليو دي higher than 13, definitely its square root also will be higher than this value.
Yes.
If you have a value less than 13, its square root also will be less than this value.
Yeah.
Right? So you can consider the square root, or you can say no, the square root will not affect the results here. لأنه if we take the square root of higher values, it will give you higher square root, and في linear or direct proportional between the this value and its square root. Okay. Okay, let us take it x square plus y square. You can resolve it by considering the square root and check the results. And this is the equality constraints here. So if you want to implement Lagrange multiplier method, you will expand this function to include this equality constraints, and you multiply this equality constraints by lambda. We have only one equality constraints. So this would be the case. You have L equal to F plus lambda G. This is F, x squared plus y squared, and this is lambda multiplied by G, and the G is the square, the circle equation. So we will take, you have here 3 variables, x, y, and lambda. So you get the derivative with respect to x, 2x, and this is gone. And you have here 2 times x minus 8. This is 0, this is 0. 2 times x minus 8 d multiplied by lambda. So lambda times 2x minus 8, and 2x minus 16. And this is equal to 0. This is the first equation. Second equation, derivative with respect to y. Again, you have 2y and lambda multiplied by 2 times y minus x, and 2y minus 12. So this is the second equation. The third equation, lambda, partial L by partial lambda. So this is 0, this is 0, and this lambda you have equal to, if you take the derivative, this will remain.
Victor,
Okay? Yes.
XY as we have two generators in our system, two generators.
Exactly, yes.
Okay.
XY are variables, and our variables in economic dispatch problem is BG1 and the BG2.
Okay.
Okay? So here, when you take the derivative with respect to lambda, this is equal to 0, and you have this only remains as such. If you look deeply in this here, this is the constraint.
Yeah.
Yani, this is exactly the constraints.
Yes.
And if we need the optimality, we have to solve these equations. That means this constraints equal to 0. That means the constraints is satisfied implicitly. يعني احنا قلنا ان السوليوشن must satisfy the constraint. مظبوط؟
صح.
And here the constraints equal to 0. So the constraints will be satisfied automatically. I hope this point is clear. يعني احنا we convert from constrained to unconstrained problem. But implicitly this constraint will be satisfied by the optimality condition here. And to get the optimal, you have to consider this equal to 0. So this is the constraints. And the constraints is satisfied now. Okay. So here you have first equation, second equation, third equation, and you have three variables x, y, and lambda. So in principle, you can solve. There is no problem of this. You can solve these equations to get x, y, and lambda. For example, you can have here x as a function of lambda. You can have here x and lambda. So you can get x as a function of lambda. So x equal to 16, or this 2 will go to this.
And y function of lambda
becomes 8 lambda over lambda plus 1. Okay. And here also you can get y in terms of lambda. So this 2 will go to 12, it becomes the same 6 lambda over lambda plus 1. And you substitute x here and y here. So in this case, you have only one equation in lambda. So you can solve to get lambda. If you get lambda from this equation, you can go and solve for x and y. Okay? So this is the procedure. So let us see. Eliminating lambda from the first two equations, you have x and y. يعني of course طبعا انت you can solve by different methods. يعني here we have here y as a function of x. يعني انت you divide, this is x and this is y, so x over y equal to 8 over 6, so becomes 4 over 3. So if you have y as a function of x, you can substitute here to get x, and then you can go back to get the others. فيعني it doesn't matter, any solution you can consider in this regard. Okay, so substituting, you can get this as a function of x, and you have here this quadratic equation in x, and you can have here two solutions, 4 and 12. So x equal to 4 or x equal to 12. And this is simply the quadratic equation. We expect and we have two roots here. For x equal to 4 or x equal to 12. If x equal to 4, يبقى x equal to 4, يبقى y equal to 3. And if y equal to 3, then يبقى this is 18 over 4, يبقى 4.5. So lambda Am I right or
That's the value of y, دكتور, not lambda.
لا يعني here if we solve and we get x equal to 4, if x equal to 4 يبقى y equal to 3. If y equal to 3 يبقى how much lambda? Or x equal to 4 يبقى how much lambda? Oh, this is the opposite. Now we have it here يعني. If x equal to 4 يبقى this is 8 and this is 8 and this is minus 16 يبقى minus 8 and this 8 يبقى lambda equal to 1. Okay, so lambda will be equal to 1. For the other equation or other solution, sorry, if x equal to 12 you can say in y equal to 9 and then you can substitute to get lambda. So you will find lambda x equal to 12 يبقى ده 24 minus 16 يبقى 8 and this is 24 and this is 8 يبقى lambda equal to minus 3, lambda equal to minus 3. Okay, so lambda equal to minus 3. So this is the equation, or so this is the minimal or the let us say this is the extrema points. هل هي local minima ولا local maxima? We have to second derivative and see, or Hessian matrix. Hessian matrix, and we get the eigenvalues of Hessian matrix. Okay, so you can continue طبعا, of course, if you want to solve completely you have to get the Hessian matrix. The Hessian matrix will be partial square f or L augmented function over partial x square partial L by partial x partial square L over partial x partial y partial square L by partial x partial lambda, and you continue here. You have 3 by 3 matrix and we have 3 unknowns, the 3 by 3 matrix. If you substitute x, y, lambda here and you get the eigenvalues of h, so this eigen will be positive, greater than 0. That means this point is minimum point. Okay, if you substitute again here with 12 and 9, you will get, and minus 3, you will get eigenvalues equal to less than 0, negative eigenvalues. In this case, you can say this point is maxima. Graphically speaking, you can, if you go back, you will find the two solutions. This solution and this solution. This solution gives you the minimum value and this solution gives you the maximum value. Okay, so these are the 2 points I identify in our solution. So you have 2 solutions here. One gives you the minimum distance, distance will be minimum value, and the other will give you the maximum distance. So this is the maximum point. Okay, I hope the things are clear. If you have any question, please ask.
Doctor.
Yes, please.
These 2 points are for sure the extreme points. يعني لو عندي مثلا مسألة ثانية أقدر أعوض مباشرة في المعادلة حقت الديستنس أو أيا كان وأشوف هو يطلع لي ماكسيموم أو مينيموم.
تاني كده معلش أنا ما فهمتش السؤال قوي. يعني
دكتور احنا الحين حددنا المعادلة اللي هي x سكويرد بلس y سكويرد، هذه حقت الديستنس اللي احنا بنشوف وين الماكسيموم والمينيموم. لو كان مثلا عندي معادلة ثانية ما أقدر بس مجرد أعوض الإكستريم بوينتس في المعادلة وخلاص أشوف إذا هي يعني طلع لي ماكسيموم أو مينيموم.
معادلة ثانية غير المعادلة بتاع السيركل؟
المعادلة حقت الديستنس اللي هي x سكويرد بلس y سكويرد.
أيوة نعم.
ايوه يعني اقصد يعني بس مجرد اعوض في الاكستريم بوينتس مباشره بعرف يعني ما يحتاج اسوي الماتريكس حقتي.
يعني تقصد انه انك انت you can just substitute by 4 and 3 لو دي الفانكشن x square plus y square you can say انه with 4 and 3 so this becomes 4 square plus 3 square so it's 25 and for 12 and 9 يبقى f equal to 12 square يعني 144 و 981 so it becomes 225. So this is what you mean? And this is maximum
Yes.
and this is minimum?
Yes.
Yeah, of course انت you can do this يعني but يعني systematically يعني يعني you have to go for the second derivative لانه ده necessary condition. اوكي؟ انما انت ما تعرفش هل البوينتس ديت هي ماكسيما ولا انفليكشن بوينت، لان في انفليكشن بوينت as we mentioned انه you can have this function and this gives you also the first derivative equal to 0. df by dx here equal to 0 also, right? But you don't know whether this is maximum or minimum. When you solve here and you get this value, you don't know whether this is minima or maxima. Could be inflection point. يعني انت متخيل معايا يعني عاوز اقول ايه؟ لو انت عندك الفانكشن بالصوره دي كده طلعت لك بوينت هنا وبوينت هنا، دي اللي هي بتديك الديستانس 15 ودي تديك الديستانس 2 او 25 و 225. سو هل دي مينيمم فاليو؟ لا مش مينيمم. هل دي مينيمم ماكسيمم فاليو؟ لا مش دي ماكسيمم فاليو. رايت؟ فانت in this case يعني having these numbers it is not sufficient to judge ان دي local minima or local maxima. معايا ولا مش معايا؟
ايوه فاهم عليك دكتور.
ف you have to go for this is called the sufficient condition. يعني when you have the eigenvalues or the second derivative is greater than 0 لا يبقى this is for sure minimum value. انما just solution of the df by dx equal to 0 doesn't guarantee ان you have local minima or local maxima. اوكي.
وايضا اتوقع طريقه مالك لو صار عندي مور فاريبلز بتصير اصعب اني احققها. احنا على 2 فاريبلز.
Yeah exactly طبعا يعني of course لو هنا يعني البروبلم is little bit easy لانه you have second order and you can graphically حتى you can solve it graphically. يعني احنا من البدايه خالص احنا ممكن لو هي بالصوره دي لو هي الكويشن بالصوره ديت احنا we can solve it graphically على طول يعني هو definitely انه the minimum value is when you have a tangent here and this tangent is perpendicular to this one. So you can graphically solve it. But if you have more variables, if you have 10 generators in your system or طبعا بنتكلم لو بنتكلم عن utility زي سعودي الكتريستيك كومباني حتى في الايسترن region you can have hundreds of generators by the way. Hundreds of generators. يعني حتى if you combine the generation plants كلها مش بس different generators لا يعني if you combine all the generating plants generators in the generating plant together as a one generator you may have like let us say احنا we have a chance or we had a chance to study this Saudi electricity company in eastern region and we were able to reduce خلي بالك reduce the generators connected to the 380 level, 380 كيلو فولت ليفل. يعني الجنريتور متوصل عن طريق ترانسفورمر ل باص 380 كيلو فولت باص. number of generators here in eastern اللي هم متوصلين دايركتلي على 380 كيلو فولت نتورك اعتقد حوالي 31 generators. خلي بالك احنا we discard all the generators connected to 115 or 230 كيلو فولت. في generators متوصلة على 115 230. We have little generators are connected on 69. We neglect all these generators connected to this network and we end up with like 30 generators connected to 380 كيلو فولت. فلو بتتكلم عن كل الجنريتورز الموجودة فهتلاقي hundreds of generators. فالبروبلم بتاع الايكونوميك dispatch in real life is not an easy. You have hundreds of variables that you need to set or to search for the optimal values. Okay, so of course you can يعني these equations, as you can see here, these equations are, you know, somehow simple equations. But if you have very complex equations here, يعني you have this here x square and x and so on, and you have non-linearities in this equation. So it is not easy to solve as we have here in this example. And here we can get x as a function of lambda, y as a function of lambda, and we substitute. Or we can eliminate lambda from here and we can get x as a function of y and substitute. But this is not always the case. If you have complex constraints and objective function, in this case, these equations are not easy to solve. So what do you think if you have some nonlinear algebraic equation? How to solve in general? How to solve a set of nonlinear algebraic equation?
Maybe
في
raise your hand please and let us be more organized. عباس فهد.
Maybe by using MATLAB or any program.
هو الماتلاب مش هيحل لك يا عباس.
دكتور
انت لازم
يمين الميثود
انت لازم تقول نعم. طبعا احنا طبعا مش هنعرف نحلها، يعني لازم ماتلاب طبعا اوف كورس. هذا ممكن طبعا لو فيري سمبل بروبلم وكان يعني دو باي هاند، انما الايه تكنيكس اللي تقدر تحل بيه انت لازم تقول للماتلاب ان انا استخدم طريقه كذا اذا كانت موجوده عنده في اللايبراري. فايه الطرق اللي بتحل النون لينير الجبريك ايكويشن؟ صالح عبد الله.
substitution method as we learn in math 2 math 1
اللي هي ايه substitution method؟
تعويض. تحط مثلا عندك x y z صف الايكويشنز تحت بعض
وبعدين
find قيمه الاكس وسبستيوت للواي.
ما هو لا ده اللي احنا عملناه في الاكزامبل ده صح؟
ايوه
مش احنا عملنا في الاكزامبل ده؟
يس.
بس عملنا في الاكزامبل ده لان الايكويشنز هنا سمبل فيري سمبل. يعني you have here two variables only, so you can get x as a function of y. You have here two variables only in this equation. If you have this x, it becomes like more complex. And you have here x, y only, so we can substitute, we can do this. But this is not always the case. معايا يا صالح؟ This is not always the case. You may have very complex problem here, the equation here, and a very complex equation here, very complex non-linear equations. Simply, and I'm asking about how to solve this equation, what are the numerical methods or iterative methods that you know that can solve non-linear algebraic equations?
Gauss-Seidel. Gauss-Seidel.
Okay, this is one. You can use Gauss-Seidel method.
And Newton-Raphson.
You can
trial
use
error دكتور مدين نستخدمه.
Newton-Raphson. This
طيب.
method I learned in 463 power system analysis. I don't know.
Exactly. Yeah, exactly. These are some of the numerical method that you can use. Muhammad Hassan, do you have a question?
No, just answer. We can use the Taylor series.
Taylor series.
Yes.
ما هي دي embedded في النيوتن رافسون ميثود. يعني Taylor expansion أو Taylor method. This is the root of the Newton Raphson method. Okay, so you can use the Newton Raphson method or Gauss method for solving the non-numerical, non-linear algebraic equations. So let us see if you have the equations are solved. You can solve the equations iteratively. In many problems, a direct solution using Lagrange multiplier method is not possible. Okay, if you have more complex problem and constraints. So the equations are solved iteratively. Newton-Raphson method is superior in such method. والناس اللي بتاخد ال 463 أكيد خدت الجاوس-سايدل ميثود والنيوتن-رافسون ميثود. النيوتن-رافسون ميثود يعني simply يعني just to brief you about it. أنت you have f of x equal to 0. Okay, you have this function equal to 0 and you need to solve. You need to find the x. Find the x to satisfy this. طبعا f of x دي ممكن تكون 3 equations زي ما عندنا في الاكزامبل اللي فات ده. اوكي طيب احنا هي الفكره بتاع نيوتن رافسون ميثود is saying that انه let us assume انه السوليوشن is x0. احنا يعني we will start with initial value. هنخمن اي قيمه ونحطها في الايه؟ في الايكويشن. بس القيمه ديت تختلف عن الاكزاكت سوليوشن باي دلتا اكس. يعني let us assume ان الاكس equal to x0 بلس دلتا اكس. يعني هنخمن قيمه للانيشال سوليوشن اللي هو x0. وهيبقى الاكس 0 ده بينه وبين الفاينل سوليوشن او الاكزاكت سوليوشن that satisfy this equation delta x. Okay, so we can say in f of x0 plus delta x equal to 0. Can we expand this by Taylor series expansion? You can say this equal to fx0 plus the first derivative partial f by partial x calculated at x0 times delta x plus 1 over factorial 2 partial square f by partial x square multiplied by delta x square and so on up to the infinity. Usually we approximate, we use only up to the first order term. We neglect it. In delta x, we expect in delta x to be very small. The difference between the initial solution and the exact solution is very small. So let us remove all these terms here. Okay. So what we have here in 0 equal to f of x0 plus this. Can we get delta x from this equation? Yes, we can say that delta x equal to minus f of x0 over the derivative partial f by partial x, but this derivative calculated at x0. So this is delta x. طيب, okay, so we start with the initial solution x0 and we found the delta x here. So let us add delta x to x0 to have a better solution, more closer to the final solution. So we can say no x now خلينا بقى first iteration here equal to x0 plus delta x here, and let us take this x1 and assume that in x1 also is different than x اللي هي final solution by delta x. So again we can incorporate it here, and we can get delta x1, which is the difference, equal to minus f of x1 over partial f by partial x calculated at x1. So this gives you the difference here, and this difference will be added to x1 to get more closer solution, which is x2 x1 plus delta x1. Okay, then what is next is to get delta x2. Delta x2 equal to minus f calculated at x2 over the derivative calculated at the most recent solution that we get, x2, and then we add x2 to x2, and then you can get x3, and you can iteratively move closer and closer to the final solution until you, of course, you reach to a certain threshold, and then you can say مثلا if delta x becomes less than مثلا 0.05, we can stop the iteration. So this is iterative methods that you at the beginning you start with initial solution x0, and then you calculate the derivative or the the increment here delta x, and you add delta x to x0 to get better solution, and you calculate delta x1 and you get better solution, and so on. So this is the one possible way of casting the last example into an iterative process. We rewrite first two equations in terms of lambda, and you can end up with f of lambda equal to this. So this is the to get lambda to have it equal to 0. Okay. So we can iteratively solve this nonlinear equation. We can say this is f of lambda equal to this, so we can get the derivative partial f of partial lambda, and we can start with initial value of lambda. Let us say take lambda equal to 2. Graphically speaking, Newton-Raphson method works as such. And I would like a space to. Okay, so. Okay, so you can hear. Here, for example, if this is if you want to search for the minimum value of this function, okay. طيب, if you start at this point and you get the derivative and you get the function at this value and you get the derivative and you get the function here and you get the derivative until you reach to the minimum value that we have. This is simply the graphical explanation of the Newton-Raphson method. At any point you assume at the beginning this is x0, you get the derivative, and then you get the function at x1, and you get the derivative, and you get the function here, and continue until you have or you reach closer to the there is no much improvement in the solution. So applying the Newton-Raphson method, this is delta lambda or delta x at iteration k equal to minus f or delta f, whatever, minus f calculated at lambda of k, iteration k, over the derivative calculated also at lambda of k. So, and once you get this delta lambda, you add it to the previous value of lambda, you get lambda of k plus 1. Lambda of k plus 1 represents better solution than lambda of k. So starting with an estimated value of lambda, and you can just initial guess, a new value is found in the direction of the steepest descent. Okay, the process is repeated until the error you have here is less than a specified accuracy. You can define epsilon and you can stop at a certain level of accuracy that you can achieve. This algorithm is known as gradient method لأنه بيعتمد على partial f partial x or derivative of this or gradient of this.
دكتور.
Yes, please.
When Newton-Raphson fails, I mean there is divergence. Maybe the first value maybe not the nearest to the right solution. So the Newton-Raphson.
والله هو النيوتن-رافسون if you compare it with the Gauss-Seidel method or Gauss method, Newton-Raphson is much better in terms of stability.
Quick. Yeah.
Very quick and also very efficient to find this. هي the problem is انه هي الخطورة هنا فين؟ خلينا نقول ان احنا عندنا هنا two values of lambda. احنا هنا lambda 1 وهنا lambda equal to minus 3. Right?
Yes.
احنا عندنا minimum وماكسيمم، يعني قلنا هنا minimum وماكسيمم، قلنا ان الفانكشن ديت عبارة عن فيه minimum وماكسيمم. مش كده؟ دي الفانكشن. ادي اللوكال مينيمم وادي اللوكال ماكسيمم. اوكي، ناو if you start لو دي لامدا if you start لامدا هير ماينس مثلا، لا خلينا نقول عشان بس دي ماينس 3 ودي 1 عشان بس تبقى فيها مصداقيه شويه، فخلينا ايه نقول ان هنا عند ماينس 3 في ماكسيمم وعند 1 في مينيمم، فادي لامدا ايكوال تو 1 وادي لامدا ايكوال تو ماينس 3. مظبوط؟ لو انت if your initial guess is lambda equal to minus 4، خلي بالك الانيشال جيس ده ايه؟ يعني كل واحد ممكن يبدا باي قيمه هو عايزها. يعني there is no criteria on this unless you know the nature of your problem at the beginning. يعني مثلا احنا في الايكونومكس باتش مثلا، في الايكونومكس باتش هنقول ان اللامدا ديت هي عباره عن انكريمنتال كوست. اوكي، فالانكريمنتال كوست ده هيبقى بوزيتيف. مظبوط؟ فاحنا المفروض ان احنا نبدا بلامدا از بوزيتيف. انما لو ما عندكش فكره عن البروبلم اللي انت بتحلها ممكن تبدا بلامدا ايكوال تو ماينس 4، واحد ممكن يبدا بلامدا ايكوال تو ماينس 5. لو بدات بلامدا هنا most likely you will hit this maximum point. You will improve the solution until you come here, right?
Yes.
But if you start مثلا lambda equal to 2, most likely you will get trapped here in this point. So you have another solution. يعني this one, the guy start with lambda equal to minus 4 will end up with minus 3. And with the guy with the start with lambda equal to 2 will end up with lambda equal to 1. This is a better solution, or this is the best solution that we'll get. فطبعا if the problem is more complicated when you start, when you have minimum, maximum, if you start here you end up with this here. If you start here you may go here, you may go here. You have to have like preliminary information about your problem in order to set the initial value of lambda wisely. Okay? Okay, so this is f of lambda, and this is the how to improve, how to get the incremental value of lambda minus f over a derivative, all calculated at the most recent value, and you continue until you have this value. So if this is f of lambda, let us solve this equation by Newton-Raphson method. So this equation is the function of lambda. So let us start derivative اللي بيسموه جاكوبيان، يعني ممكن ده نقول عليه جاكوبيان اللي هو الديريفاتيف اوف لامدا. Okay, derivative of lambda is equal to minus 200. If you take the derivative of this, you will end up with minus 200 over lambda plus 1 cube here. So this delta, this is a general formula of delta lambda, and this is the general formula of the of the recursive formula of lambda of k plus delta lambda of k plus 1. So you can of course start with lambda equal to 0.4 مثلا. Let us start with the initial value lambda equal to 0.4. For that specific problem, if you start with 0.4, معلش قايلينها هنا, if you start with 0.4 يعني at this value, right? So most likely you will end up with lambda equal to 1 is the best solution. لأنك أنت you start very near to this. Am I right?
Yes.
Omar Abdurrahman, do you have a question?
Yes, I'm asking about number of iteration. Is it depend on the specified error only? I mean,
Tolerance.
once
Yes.
I meet the error,
Yes.
I stop.
Yes. You can say no if the difference between lambda of k plus 1 minus lambda of k less than, يعني there is no much improvement, less than 0.05, I will stop. Somebody say لا يعني here you have to compromise يا عمر between the number of iteration and the speed of computation. لأنه do you need more accurate value or you need a rough solution? لأنه some of the problems in power system you need more accurate value. So لا يعني you can reduce, especially for steady state solution, steady state problems. Time is not an issue. For steady state problems, time is not an issue, big issue. فأنت you can reduce this 0.05. Okay, gives you مثلا 10 iteration. If you make it 0.01, this will give you like 50 iteration and so. If you need rough solution, لا يعني you can increase this to reduce the number of iterations.
Yes.
The number of iterations depends on the, of course, the accuracy level that you have. If you look at this, we start with lambda equal to 0.4. We get f equal to 26.02, derivative equal to minus 72, and we substitute here to get it delta lambda becomes 0.357. We start lambda equal to 0.4 and this delta lambda equal to 0.357. So lambda 1 equal to the summation 0.357 plus 0.4, so it is 0.757, right? Is it clear? احنا we substitute here, احنا جبنا delta lambda of k plus 1 equal to lambda of k plus delta lambda. فانا we solve here based on this delta lambda, lambda 0.4, we substitute, we get the derivative, we divide, we get delta lambda equal to this. So how much lambda 1 now? This is lambda 0. This value is lambda 0. Lambda 0.
Lambda 1.757.
This is lambda 1. What is lambda 1? Lambda 1 is a summation of delta lambda plus lambda. Lambda 0 plus delta lambda 0 gives you lambda 1. With this lambda 1, you go and substitute here to get how much the function, how much the derivative. You divide this by this, you get delta lambda here. If you add this delta lambda with lambda, this is delta lambda 1. Now, this is delta lambda 1. If you add delta lambda with lambda, you get lambda 2. With this lambda 2, you get the function, you get the derivative, you get delta lambda 2. And you add this with this, you get lambda. And as you can see, we approach the best solution, which is 1. We start with 0.4. Iteratively, we have 3-4 iteration. We end up with lambda equal to approximately 1. Okay?
دكتور
Yes.
اللي يبدا بلمدا 0.9 الايتريشن بيقل number of iteration
لامدا ايه؟
لو بدينا بلامدا 0.9
0.9
yeah
of course الايتريشن بيقل. لو بديت بلامدا ايكوال تو 1
I think it will diverge the solution right
ليه يا عم؟ دايفيرج بتقول ولا كونفيرج؟
لا diverge
ليه؟ ده انت بادئ عند الحته اللي احنا عايزينها، فلا هتروح يمين ولا تروح شمال. يعني لو بدات ب1 هيبقى زيرو ايتريشن، لانك انت لو بدات ب1 يعني لو انت يعني فيري لاكي، يعني انت عندك لو نون لينير ايكويشن وحطيت اللامدا مثلا باي فاليو وهي الاكزاكت سوليوشن، فخلاص يعني you will converge at the beginning. here lambda equal to 1 you will substitute، هتلاقي ان الفانكشن equal to ايه؟ to 0. ما ده اللي انا عايز احله، ده اللي انا عايز اجيبه. if you substitute here with lambda equal to the exact solution you end up with f equal to 0. You are very lucky in this case. There is no iteration. Okay, so the closer the solution, of course, the lower number of iterations. هادي علي, do you have a question?
طيب دكتور، على اي اساس اختار اللي هو اول لمده اسويها في الفورمولا؟ يعني كيف يكون الرنج حق اللمده اللي اختارها في البدايه؟
ما هو ده اللي احنا بنقوله بقى، انك انت you have to have like some background about your problem. البروبلم اللي انت بتحلها. يعني مثلا احنا بنحل مساله الايكونوميك ديسباتش. اوكي؟ اللامدا دي زي ما هنعرف بعد كده ان هي دي الانكريمنتال كوست. فالانكريمنتال كوست بتاعك هل هو بوزيتيف ولا نيجاتيف؟ يعني هل الكوست ممكن يبقى نيجاتيف عشان تولد ميجا وات اور نديك فلوس، ولا انت تاخد منا فلوس؟
انا اخذ فلوس
طبعا اكيد طبعا يعني ديفينتلي. فالمفروض الانكريمنتال كوست بوزيتيف، فما فيش معنى انك انت تبدا بايه؟ بنيجاتيف فاليو، فنبدا ببوزيتيف فاليو. طب وات وود بي ذا يعني رف estimation of this lambda؟ مثلا نحطها مثلا 200 300 بالميجا وات اور؟ لا طبعا very expensive، ما ينفعش الكلام ده. يعني انت لو شركه الكهرباء بتبيع لك الكهرباء بكام؟ 17 سنت او 17 هلله بير كيلو وات اور، رايت؟ مظبوط ولا مش مظبوط؟
يس.
طيب الميجا وات اور يبقى كام سعرها؟ الميجا وات اور، الميجا وات اور سعرها كام؟ لو ضربت دي في 1000 كيلو يعني ميجا، لو ضربت دي في 1000 يبقى 17 هلله في 1000 يعني 170 ريال مثلا، مش كده؟ 170 ريال اوفر ميجا وات اور. يبقى ادي عندنا ديت الايه؟ اللامدا approximately يعني roughly speaking يعني around 170. انما ما نبداش ب 1000، ما نبداش بنيجاتيف فاليو كده، بنطول الايه؟ النمبر اوف ايتريشنز، وممكن يحصل دايفرجنس وتروح في حته ثانيه. فيعني you have to have يعني some background about the problem you are solving in order to you know minimize number of iterations. Okay?
هذه نفس الفولتج at each bus النومينال 1 per unit.
Exactly. This is the case also for the you know load flow problem. In solving of the load flow problem, you يعني expect in the voltage to be around 1 per unit. So you can also start with voltage equal to 1 per unit. So this is the wise start. انما طبعا ما نبداش بفولتج equal to 0.2. This is يعني unreasonable يعني. اوكي؟ Is it clear يا شباب؟ عندنا مالك علي. Do you have a question يا مالك؟
Yes, Doctor, I'm curious if you choose a point of lambda that is exactly between the 2 points. يعني بالنص بالضبط. يعني لو مثلا في الاكزامبل حقنا اخذنا لامدا يساوي -1، وين راح يروح الايتريشن؟ اي نقطه؟
والله وين يروح بقى يعني هو طبعا يعني وين يروح انا مش عارف، لازم we have to iterate يعني الا اذا يعني كان في some يعني يعني الفانكشن could be لو انت هنا عندك -3 ودي اللوكال ماكسيمم ودي -1 local minima، فانت if you start here you may go this way or you go this way. يعني you have to start and see. There is no guarantee. النيوميريكال solutions او النيوتن رافسون ميثود او جاوس سايدل ميثود ممكن يحصل divergence للسوليوشن، مش لازم في كل مره يحصل ايه convergence وتصل للاوبتيمال بوينت، ممكن يحصل divergence. ف this is يعني some stability problems of such numerical techniques يعني. of course you start wisely and then you can iterate and see the best solution. Do you have any question? I think the time is over. Let us stop here. And yeah, this is now we will implement this optimization techniques on economic dispatch problem. We will start this next class, inshallah. If you have any question, please stay with us. Otherwise, you can leave this. I will stop recording here. And of course, you can